Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear. This is my continuing feature on the Math Lovers book. And last time I talked about, one very useful tool for doing logical arguments, and those are known as logical identities. Today I'm going to talk about another related tool. These are called rules of inference. We use these as well in logical arguments. So anyway, let's begin. So, what is a rule of inference? Well, it's a little bit different in form from a logical identity. A logical identity always has a form F is equivalent to G, where F and G are logical expressions. They could be either atomic or compound logical expressions. But a rule of inference is it starts with a set of premises, which I'm calling P1 up to Pn here, there's a conclusion that follows from these premises. So it's basically sort of a logical sub-argument. I mean, there's very, they're kind of obvious logical arguments. They're sort of the tools, for the kind of basic logical arguments that you can use in bigger logical arguments. You can think of them that way. But there's usually only two or three premises. Anyway, and another way you can write them is you can write them as one single tautology. You can say P1 and P2 and so on all the way up to Pn implies C. That's equivalent to this logical argument I'm just showing you here. Anyway, so anyway, now all I'm going to do is I'm going to show you 12 very useful rules of inference, which are often used in logical arguments. So I think the one that's most well known is called modus ponens. I think that most of these have Latin names. I said last time I said the logical identities have Latin names. I don't think any of them did actually, but these do. So anyway, modus ponens. You start with if P then Q. That's your first premise, and then your second premise is P, and your conclusion is Q. I think this is pretty obvious. If P then Q always means that whenever P is true, Q is true. So whenever you start with if P then Q, and then you have P, obviously you have Q. So I think that one's kind of obvious. Then you have kind of the converse of that, rule two, uh, modus tollens. And in that one, you start again with if P then Q, but now instead of your second premise being P, it's not Q. So you're saying Q is false. Well, if Q is false, then P has to be false. And why is that? Because remember, if P then Q, the only case that's false for that is P being true and Q being false. So if we know P is Q, it follows that Q is true. That's modus ponens. But if we know that Q is false, it follows that P is false. That's known as the converse. So anyway, you can think of modus tollens as the converse of modus ponens. Anyway, so that's another important one. And then rule three, law of biconditional propositions. This is kind of a definition of equivalence. Remember, I said that P is equivalent to Q whenever P implies Q and Q implies P. So if your first two premises are P implies Q and Q implies P, then we automatically conclude that P is equivalent to Q. Okay. And then rule four, this one is called um, uh, ex- exportation. So this one's a little more they get a little more complicated, but here we're our first premise, we just have one premise here, and that one is P and Q implies R. So if P and Q implies R, then we conclude that P implies the implication Q implies R. I don't think this one's as obvious, but it's kind of like a chain of implications. I guess you can think of it. Maybe it's easier to give an example. So let's say if I eat breakfast, if I eat a good breakfast and I prepare for my lesson, then I'll have a good lesson. That's equivalent to saying if I eat my breakfast, then if I have a good lesson, then what did I say? If I eat a good breakfast and I prepare my lesson. So if I first eat a good breakfast, then if I prepare my lesson, then I'll have a good lesson. I think you can see those are the second one follows from the first. So you're just replacing your and at the beginning by a chain of implications. I think the more you use these, the more obvious they'll get, by the way. The fifth one is called absorption. And this one, I don't think this one's too hard to understand. Or no, I get the wrong one. Yeah. No, the next one's called transposition. Rule 5. So you start with if P then Q, and then you conclude that if not Q, then not P. This is a little like modus tollens. It's a little like modus ponens and modus tollens combined. It's just another kind of equivalent formulation of implication. So we say if P implies Q, then it's also true that not Q implies not P. I think that's kind of obvious if you think about it. I mean, it's almost like what we were doing from going from modus ponens to modus tollens. I think the thing on the bottom is called the converse. Maybe just think about it that way. So you have an implication on top, P implies Q, and then the converse of that implication is not Q implies not Q. Maybe it's good to do an example. If I eat a good breakfast, I'll be in good shape. If I'm not in good shape, that means that I didn't eat a good breakfast. I think you can kind of see how that works. All right. Rule 6. This one's called hypothetical syllogism. Okay, I don't know why it has that name, but this is just a chain of implications. So if we have two implications, P implies Q and Q implies I, then it follows that P implies R. I think that one's kind of obvious. Just think of implications as like a chain of cause and effect. So, if I, think about this as like a little machine. If I push the button and the machine starts, and if the machine starts, a bell will ring. So that means if I push the button, a bell will ring, right? Just a chain of events. Okay. So anyway, rule 7. This one's called absorption. So we start with a simple implication, P implies Q, and then we conclude that P implies both P and Q. I think this one's kind of obvious, because P always implies P. So adding P to the right side doesn't really change anything. I mean, let's give another example. If I eat a good breakfast, I'll be in good shape. That implies if I eat a good breakfast, I'll have eaten a good breakfast and be in good shape. But adding the part that I've eaten a good breakfast doesn't really add any information. So I think you can kind of see how that works. Rule 8. This one's called disjunctive simplification. I think the names are kind of harder than the actual rules of inference. But so you start with P and Q, or P or Q. That's a disjunction, and then you assume not P, and your conclusion is Q. Well, that almost like a definition of or, right? We're assuming that either P is Q or Q is true, or P is false, and it's obvious the case that Q is true, right? Because one of them has to be true. We've just ruled out P. So rule 9, addition. And this one's kind of obvious too. We start with P, and we automatically conclude P or Q. P is already true, so you can or it with whatever you want. Remember, or only cares about one thing being true. So once we've already established that the first thing is true, it follows that this disjunctions are true. It doesn't care about Q at that point. And then this one's kind of simple, kind of similar, but it involves and, rule 10. P and Q implies P. Well, that's true because both P and Q are true. Right. I guess we could add another rule. P and Q applies Q, but you don't really need that one. You can use the commutative property of conjunction along with that. So you kind of get that one for free. That was a logical identity. Remember, P and Q is equivalent to Q and P. So if we wanted to prove that P and Q implies Q, what you first do is you use the logical identity P and Q is equivalent to Q and P. So then you could automatically write down Q and P, and then Q and P implies Q, because we're just switching around the roles of P and Q. You'll get used to doing this as we do more of this, but anyway. Rule 11. This is called conjunction. So we just start with 2 two premises, both P and Q, and we conclude that P and Q. Well, that's pretty obvious. Remember, we're assuming that P is Q, and then we're assuming Q is true. So it obviously follows that they're both true. That's what P and Q means. And the last one I have here is called resolution. This might be the most complicated one on this list, but I don't think it's too bad. So we start with P or Q, and then we have not P or R. And the conclusion is Q or R. Let's see if we can make sense of this. Yeah, this one I don't think is so obvious, but let's try an example. Maybe it'll make a little more sense. Okay. I'm trying to think about this. Okay, either the Reds or the Yankees will win the World Series, and then either the Reds will lose the World Series or the Dodgers will win the World Series. And we conclude that either the Yankees will win or the Dodgers will win. Is that obvious? I don't know if that's so obvious. How do we conclude that? I'm not even sure. Yeah, like I said, this is the most complicated one. I don't even know if I can think of a simple example that makes this one obvious. But I guess maybe we could do it by converting these implications. So remember, not P or R is the same thing as P implies R. Will that help? And then not P or Q is the same as not P implies Q. So we have not P implies Q and P implies R. Does that help? And then we conclude that not Q implies R. I don't know how that works. I don't know. I'm not going to try to figure this one out. That's probably the most complicated one on this list. But anyway, this is a list of 12 rules of inference, and it's a little bit of an arbitrary list. When I first learned logic, I only learned 9 rules of inference. I don't think I learned 12. You might be able to do that with that one. But anyway, it's just a simple little list, and now I've given you pretty much all the tools you need for doing logical arguments and propositional logic. And the next lecture, I think the next lecture will be kind of fun. I'm going to give, I think, 3 examples of logical arguments with actual statements in them, where we can actually prove something. And I think this will be fun because we'll use these logical identities and rules of inference as tools to make logical arguments. And I think this is kind of fun. You're kind of reducing deduction to math, and you do a lot of deduction. Think about this as a criminal trial. I mean, that's what the judge tries to do, or the jury tries to do. You listen to all the evidence in a court case, and you try to come up with a verdict. But if you're logical, imagine that your jury knows logic. They know propositional logic. They can write down all the information they heard in the trial, assuming that it's all true, and you have cross-examination to try to, rule out lies. But assuming that all the information you've heard in the trial is true, you could write it all down, and you could, try to prove the conclusion. Either the accused is guilty or not guilty. Think about it that way. So I don't think juries usually do this, because most of them, I don't think, have ever had a class in symbolic logic. Maybe it would help if they did. I don't know. But anyway, so that completes my video for today on rules of inference. Thank you for watching. Long live math, and I'll see you guys next time. Bye.